Okay, and last but not least, our last part relevant for the exam, which is spatial temporal data, also sometimes called trajectory data. So spatial temporal data is about time series where we record the spatial location of something, some objects, over time. So in that case, they are basically special cases or special instances of time series. And transitively, so to say, special instance of sequences. So we have sequences of spatial locations of objects, and of course we want to somehow get some patterns out of these sequences, time series of spatial locations. We just will feature some high-level methods and challenges. We don't go into details too much, but hopefully it gives you a kind of flavor, kind of feeling what is going on when you, or what can you do when you want to analyze spatial temporal data, trajectory data. And you will see that as you see it in the outline, there are geometry-based approaches and semantic-based approaches, and we'll first of all discuss what is the difference between those. Okay, so starting with that, first of all, what I just said, spatial temporal data is a special case of time series where the information recorded at each time point is the spatial location of some object, and these time series over spatial locations, spatial temporal data is typically called trajectory data. Yeah, so we're talking about trajectories. One object is a trajectory of an object, actually. Often there are some additional information on different time slots, for example, semantic information on the location. So not only GPS coordinates, but also some semantic information like here is a museum, or here is an airport, or whatever. So the trend is to enrich spatial temporal information with more semantic information, like information on the location, information on what has been done at that time slot, at that location. For example, chat with a friend, or having a nap, or whatever. The field of mining spatial temporal data is very, very broad. So the lecture, what I just said, is just a very basic snapshot of the field. Absolutely incomplete. There's no claim that we are complete here, but just that you know. And we try to get the more general major approaches to trajectory mining and trajectory analysis, and that is geometry-based approaches and semantic-based approaches. And we'll have some kind of the basic ideas of both of these major approaches, basically. So what is geometry-based and what is semantic-based? Well, geometry-based approaches, that is left here, consider only the geometrical properties of trajectories, obviously. So for example, we focus on so-called location-based similarity. So we only care about of course the temporal domain, but especially about the spatial location at the particular time slots. If we have more than just the spatial locations, as I just said, that we enrich these information with additional semantic information, if we do have that, then we can also focus on semantic-based methods that try to compute patterns based on the semantics of the data, sometimes independent of the specific spatial locations, because an airport can be there and there, so it's not so important if you are at that particular airport. It's only important if to be at one airport somewhere. And that is different to the geometry-based methods, where it's important to be at the same airport, at the same GPS coordinates actually. So that is the basic difference. And forget about these system architectures. The only thing is that here you enrich the whole thing with application-specific semantic data. So that is the basic idea. And if you have that, you probably want to make use of it when it comes down to analysis. So the basic difference, once again, is here you only look at specific locations. Here you also or only look at the semantics of the locations. So here really the GPS coordinates or whatever coordinates you record are important. Here it's more about the semantics that you get. For example, the semantics of the locations you are. And of course, there may be different coordinates with the same semantics other than here. Yeah, so you will get different patterns here than here, obviously. Yeah, so let's first have a look at geometry-based trajectory mining, and we start with one of the pioneering approaches, basically, which is a paper by Laube et al., very, very high cited. The authors actually proposed 5 basic patterns which are based on location, based on GPS coordinates or any coordinates, in addition to direction of movement and or movement at all, because we are talking not about only about spatial data, but also about spatial temporal data. So we know the movement and the direction of movement of the objects because we consider spatial locations over time and the change of spatial locations over time. Yeah? So 5 basic patterns based on location, direction, and movement, and of course there have been several extensions proposed to these patterns over time, but we will just mention the 5 basic ones. You will find out that all those patterns are basically about some circular region of radius r. Yeah, so which probably makes sense because we're talking about spatial locations. So all these patterns are based on a concept of a circular region with specific radius, and something has to happen inside this circular region. And let's see what can happen. Well, convergence means, it's probably the simplest way, or the simplest pattern is at least m entities pass through this circular region of radius n r, regardless of time. Yeah? So this is probably the most simplest version of a pattern, meaning that there is some kind of circular region and all these trajectories pass through this region regardless if it's the same time frame or not, yeah, regardless of time, so to say. And if those here are more than m is another threshold, so it's kind of density-based threshold. Yeah? R is the radius of this region, and m is a minimum number of entities, objects that have to pass through with their respective trajectory. Yeah? So that is convergence. Reoccurrence is that at least m entities visit a circular region of radius r, again at least k times. Yeah, so it's conversions that reoccur. Yeah, obviously. So these trajectories visit the particular region more than k times. Yeah, so for example, more than k time slots can be subsequent time slots, of course, can also be not subsequent time slots. So recurrence need not to be subsequent k times slots, yeah, but it need to be at least k time slots. So it is a little bit more specific than convergence. So it's convergence, but at least k times, yeah, for each entity. But in the end, it's more or less the same, yeah. But the reoccurrence point is the at least k times. Yeah, then what can we do else with this circular region with radius r? Well, encounter means that at least m entities are inside the same region, assuming that they move with the same speed and direction. That could be, for example, a traffic jam at some moment if cars keep moving in the same direction but with the same speed. Yeah, so that is an encounter inside the same region, at least m entities moving with the same speed and direction. Yeah, so that here maybe would be a kind of encounter if they all move in the same direction. Yeah. Then a leadership would be at least m entities are within the same region, so a kind of encounter, but one of the entities is heading the direction for at least t time steps. Yeah, that could be, for example, modeling a bird migration. So this one here makes a leadership out of an encounter. Yeah, so we have an encounter here, and one here is the leader, so to say. So one is heading in the same direction at least for t time steps. Yeah, so these time steps here may be t, so that is the same direction as the others here. We have an encounter, and one is going in the same direction as the others for at least t time steps, which is the leader here. Yeah, so and all the others follow basically. That is the intuition of the bird migration here. Yeah, and finally you have flock patterns. So at least m entities are within the radius region, yeah, and move in the same direction during a time interval smaller than s. That is typically also a traffic jam. So that may here in that case may also be a flock pattern. So here you constrained an encounter to be during a given time interval. Yeah, so that is the most specific pattern, probably flock pattern, and very often you are interested in computing flock patterns. And there are many different ways how you can try to, or many different approaches how you can compute the different these different patterns proposed by Laube et al. So Laube et al. Basically proposed those patterns, also try to propose some algorithms to compute them, but that is actually the pioneering work, and there are a lot of follow-up extensions to these patterns, but especially also follow-up work how to efficiently compute these patterns actually.